Hi, I'm Dr. Jim Overholt. I'm the Senior Scientist for Autonomous Systems at the Air Force Research Laboratory, and today I'm joined by Ms. Chris Kearns, the Portfolio Manager for Autonomous Systems at AFRL, and together we're going to talk to you about the technology strategy for autonomous systems and autonomous science.
So we've talked to you a few times about, in previous versions, about our vision and our strategy and the goals that we've laid out to structure our autonomy program here in the Air Force Research Lab. We're going to briefly go through that, and then we're going to dig into one of the goals that we haven't talked about yet. So our vision, like we've talked about before, is about intelligent machines seamlessly integrated with people. So again, we're not talking about taking people out of their roles, but we are talking about making intelligent machines that we can integrate with people so that we maximize performance in the complex contested environments that our military has to operate in. And when we take that vision and we say, so what are the major challenges, what are the goals that we need to try to achieve in order to realize this vision, we break those into four. The first is about demonstrating highly effective human-machine teams. So again, how do you put people and machines together and get them to work together well? The second one is about creating coordinated teams and machines. So just like we want people and machine teams, we want machine and machine teams.
Absolutely.
Third goal is about getting these systems to be able to operate in complex contested environments that we operate in. And then finally, and underlying that, our fourth goal is about making sure that these systems operate safely and effective. In other words, how do we test and evaluate, verify and validate systems that are going to think and make decisions and do things on their own. So we previously have talked to you about the highly effective human-machine team goal. Today, we're going to take on and talk about this coordinated teams and multiple machines and our ideas and our thoughts and the challenges that we've identified in how do we create these teams and machines that can work together and coordinate and perform their mission.
So with what we talked about before was this notion of enduring problems. So in the effective human machining, we talked about enduring problems, and certainly when it comes to coordinating teams of machine, there are enduring problem space. And one of the first ones is this notion of machine intelligence. But this idea of machine-to-machine intelligence, how machines tackle problems, how they can think, how they can basically come together and be able to coordinate their movement and be able to apply their particular resources to a problem that they are having to face. And that's one of the most significant things we're looking at. The second enduring problem is this notion, if we have these teams of machines, in some cases we're going to want them to be able to change and fractionate or be able to take their, if they go from 10 down to maybe groups of 4 or 5, be able to tackle a problem or be able to distribute to handle certain tasks. That's going to be a real key feature. So not only the intelligence in the machines, but the ability to redistribute the collective, so to speak, and be able to tackle the machines. And the final enduring problem that we're trying to look at when it comes to scalable machines is this notion of how do we facilitate excellent, good, reliable communications all through this phase, because now you're going to have machines that need to communicate with each other and not just traditional communications. So we'll use any kind of modes and modalities that are available to us. So to us, those are the enduring problem space for really trying to realize this notion of coordinating these scalable machines together.
Yeah, so if I can add to what you just said, is it's really about, so how do we create a single intelligent machine that can sense its world, can understand what that means, understands commander's intent, and then can take action. It can decide and it can take action and knows what the appropriate action is.
Very right.
So on its own, it can do that. Now let's take one platform, put it with other platforms, and now they need to come together and they need to plan based on what their mission was, what their commander's intent said to do, go out, perform their individual missions, be able to coordinate, come back together, do things as they need to do things, and be able to do that in that communication and secure communication so that they know that where each other are and where they're at, what the state of the mission is.
All excellent points. Like you said, one machine is difficult. Now we're going to look at multiple machines.
Right, and make sure they behave themselves. So one of the underlying technologies, I think, in that is today's platforms in the Air Force. We are taking thousands and thousands of data points on how subsystems are performing.
Absolutely.
You know, what's the hydraulic pressure, what's the engine temperature, how is this the boards performing inside the electronics. But in today's systems, we don't do a very good job of turning that into real-time state.
Yes.
The machine does not understand, so based on these sensor readings across its subsystems and the platform itself, what does this mean I can do? And can I report that says, hey, here's how much further I can fly, here's a maneuver I can't do, there's a resource within the intelligence capability I can't provide right now because I'm being tasked to do other things.
Right.
So what we would say is what we'd like to see is systems that are aware of their own state, that they can take all of this data and not turn it into knowledge about its state, what it can do, what it can't do. And this is important so that if a person is sitting there, it isn't, I really don't care what the hydraulic pressure is, the engine temperatures necessarily. What I really care about is what does that mean that you're going to be able, the system is going to be able to do to help perform the mission that we have.
What the performance, the actions of the machine, right.
Right. So that is one of the underlying, when we talk about autonomous systems, I don't think it comes out, and we don't highlight it a lot across the community, but it is going to be a key technology enabler in order for us to have systems that behave and act on their own.
So self-awareness is what you're looking for through the application of doing that kind of state measurement.
Absolutely. And then when you say, well, that's one system, again, now it needs to be able to communicate that to a team. So if something happens in the, in the military mission, if it gets shot at, if something happens, it can report back to its teammates what it's capable of doing. Absolutely. So that then they can readjust to figure out how to perform their mission.
So an application of this kind of technology is something that we'd be looking at, which would be manned-unmanned teaming. So we envision a future, certainly we're looking at intelligent machines, a single intelligent machines. Now we're looking at collectives of intelligent machines, but the real key piece is how do we integrate manned systems into this collective of unmanned intelligent systems. So that's going to bring about its own challenges in terms of being able to coordinate, distribute tasks, be able to assign to the unmanned systems what they need to do either from a human commander and or being able to self-organize and be able to distribute in order to handle a particular problem or issue that they're dealing with. So one of those particular significant problems we're looking at is this notion of a manned-unmanned wingman. So a manned-unmanned wingman is the kind of thing that we're interested in looking at, where you could have a piloted aircraft that is supported by unmanned assets, and then they have some kind of mission they're trying to accomplish, and be able to distribute the task based on what the desired mission content or mission outcomes are. And so this is something that folks at AFRL are looking at right now in terms of what are the technologies, what's the intelligence of the machines, because obviously we want these machines to be able to follow commander's intent. We want them to be able to disperse and do what they need to do, and there's going to be some amount of learning in this process as well. In other words, as the machines go out, they understand, again, back to our other things we've talked about, the tendencies of the human that they're dealing with, understand how to tackle the problem in the best way possible.
So what I think we just laid out is some of the ideas, some of the foundations and our enduring problems for this coordinated teams of machines. We've previously talked about what the highly effective human-machine team is. So we will, in the future recordings, talk to you about the complex contested environments, as well as TEV&V, or these safe and effective, making sure the things operate safely and effectively. And so with that, we're going to wrap up this one, and we'll come back and we'll check in for what we've got for the other two goals. If you haven't already seen the previous two, please tie in and check those out too.
Thank you very much.